Hey guys, Mr. Backerberg here. In this video, we're going to take a look at logarithmic functions. So as we're looking at logarithmic functions, the base A logarithm function y equals log base A of x is the inverse of a base A exponential function y equals a to the x, as long as your a value is greater than 0 and it's not 1. Now, as far as the domain and the range of a logarithmic function, the domain of log base a of x is from 0 up to infinity, but not including 0. And the range is going to be from negative infinity to positive infinity. So that would be all real numbers. Now, there are a couple of special kinds of logarithmic functions. Logarithms with base 10 and base e are especially important, and they have their own special names and notation. So the first one is a base 10 logarithm, which is also called a common logarithm. With base 10 logarithms, we don't typically write the base of 10 down there. So if you see just the log of x, that's an implied base 10 logarithm. The other special kind is a natural logarithm, which is a base e logarithm, and we denote that as just ln of x. So that's the natural log of x. Now, there's a few different properties that we're going to be looking at for logarithms, and the first one is just the inverse property. And this deals with the fact that exponentials and logarithms are inverses of each other. So for base a greater than 0, as long as a is not equal to 1, if you have an exponential function, base a raised to the power of log base a of x, because that a exponential and log base a are inverses of each other, they would cancel each other out, leaving you with just x as your answer for x values that are greater than 0. And if we look at that the opposite direction, if you have log base a of an a-based exponential, again, that log base a and that a exponential would cancel each other out because they're inverses of each other, leaving you with just x. And that works for all x values. Now, similarly, we have a base e version as well. So if you have e being raised to the natural log of x, remember natural log and base e exponentials are inverses of each other. So those cancel out, leaving you with just x for x values that are greater than 0. And if we look at that the opposite direction as well, if you do the natural log of a base e exponential, those will cancel each other out, leaving you with just x again. So we're going to look at a couple examples where we are solving an equation to get x alone. So this first equation says that we have the natural log of x equals 3t plus 5. And I want to get that x alone. Right now I'm doing that natural log to the x. So if I want to get rid of that, the inverse of that natural log is going to be taking this and putting it as a power on an e exponential. But whatever we do to one side, we have to do to the other side as well. So I'm going to take that 3t plus 5 and put that up as a power on an e also. Now on the left-hand side, that base e and that natural log cancel each other out, so we get x equals. On the right-hand side, we don't know what t is, so there's not a whole lot of simplifying that can happen there. So it's just going to be e raised to the 3t plus 5 power. We have solved to get x all by itself, which was our goal, so we're done with this one. Taking a look at this example, we want to solve this equation for x by using that inverse property again. So we've got e raised to the 2x equals 10. Because that 2x is up as a power on that e, to get rid of the e, I want to do the natural log, because that's going to cancel that out. But whatever I do to one side, I also have to do to the other side. So on the left-hand side, the natural log and the e cancel each other out, leaving us with just 2x equals. On the right-hand side, we get the natural log of 10. I want to solve to get x alone, so I'm going to divide both sides by 2. So I'm going to get x equals 1/2 times the natural log of 10. Now I could type this into my calculator and get a decimal approximation. If we did that, it would be about 1.15. So that's going to be our answer for this one. A few more properties that we're going to take a look at. So for this to work, we're going to let x be some number greater than 0, and also y is going to be some number greater than 0. The first rule we've got is a product rule, and these will hold true for any base a. So if you have log base a of x times y, the product rule says that you're allowed to split that up into two separate logarithms using addition. So log base a of x plus log base a of y. Now similarly, we do have a quotient rule. So if you have log base a of x divided by y, we can split that up. Multiplication turned into addition, so division is going to turn into subtraction. So it's log base a of x minus log base a of y. And then our third property is the power rule. So if you have log base a of x raised to the y power, the power rule says that you can take that y power and drop it down in front of your logarithm as a constant multiplier. So y times log base a of x. Next thing we've got is what's called a change of base formula, and this helps us with graphing out logarithmic functions using our calculator. Not every calculator will let you type in different bases of logarithms. So in order to use a change of base formula, there's actually two different ones. So if we have log base a of x, we could rewrite that as a fraction, log of x divided by log of whatever that base a is, but it also works for natural logs as well. So we could just do the natural log of x over the natural log of a. So in this example, we're going to use those change of base formulas to graph out the function f of x equals log base 2 of x. And I'm going to graph these out on my calculator. Now my calculator will actually let me type in different bases. So what I can do here is if I hit math and then arrow down until I get to log base, we're going to be graphing out log base 2 of x. Now I'm going to show you that all three of these give you the exact same picture. So our first change of base formula said that we could just do log of x divided by log of the base, so in this case that's 2, or we could do natural logs instead. So I could do the natural log of x divided by the natural log of that base 2. And again, I'm graphing out all three of these just to show you that they are equivalent pictures. I'm going to do zoom 6 to get my nice 10 by 10 window, and I can see that as I graph these out, all three of my lines overlap each other. So that shows visually that they are equivalent. In this example, we're going to be taking a look at how long it takes a savings account to mature to a certain dollar amount. So Sarah invests $1,000 in an account that earns 5.25% interest compounded annually. And we want to figure out how long it's going to take for this account to reach $2,500. So our compound interest formula is a equals p times 1 plus r over n to the power nt. Now remember, p stands for the principal amount. That's your starting investment. So that's our $1,000. Then we've got 1 plus the interest rate as a decimal is 0.0525 over n is the number of compoundings. We're doing this annually, so it's just 1. And then as far as the power goes, n is 1 and we don't know t, so 1t would just be a power of t. Now on the left-hand side, we know what this a value is. We want our account to get to $2,500, so I'm going to plug that in on the left-hand side. Now before I get to the actual solving portion, I'm going to clean this up just a little bit. Inside of those parentheses where we're taking the 0.0525 and dividing by 1 isn't going to change that at all, so I'm going to take that and add that to the 1. So we're going to have 2,500 equals 1,000 times 1.0525 raised to the t power. Now our goal is to solve to get t alone. The very first thing that I'm going to do is take that 1,000 and divide that over to the left-hand side. So we're going to get 2.5 equals 1.0525 raised to the t power. Now having t up as that power makes this a little bit complicated. So it would be nice if I could bring that power down. Well, when we talked about logarithms, we had a power property that said if you're doing a logarithm of something raised to a power, you're allowed to drop that power down. So what I'm going to do is actually take the natural log of both sides here, and then if I look at what's happening on the right-hand side, I have the natural log of something being raised to a power. So my power property is going to let me drop that t power down in front of this natural log. So I've got the natural log of 2.5 equals t times the natural log of 1.0525. Now I want t to be alone, so to get rid of this multiplication, I'm going to divide this natural log over to the left-hand side. So I end up with t equals the natural log of 2.5 divided by the natural log of 1.0525. And then what I can do is I can take this right-hand side and type that into my calculator to get a decimal approximation. If we do that, we're going to get 17.9. Now we're talking about a time, and in this formula, time is being measured in years. So this is going to take almost 18 years for our account to reach $2,500. That's going to be it for this video. Thanks for watching.